Welcome all students to the course of Data Communication and Networking. We start our discussion of the internet model with the bottommost layer, the physical layer. It is the layer that actually interacts with the transmission media, the physical part of the network that connects the network's components together. This layer is involved in the physically carrying information from one node to the network to the next. The physical layer has a complex task to perform. One major task is to provide a service for a data link layer. The data in the data link layer consists of zeros and ones organized into frames that are ready to be sent across the transmission medium. This stream of zeros and ones must first be converted into the another entity called as a signals. One of the service provided by the physical layer is to create a signals that represent in a stream of bits. The physical layer must also take care of a physical network, the transmission medium. The transmission medium is a passive entity. It has no internal program or a logic for the control like other layers. The transmission medium must be controlled by the physical layer. The physical layer decides on the direction of the data flow. The physical layer decides on the number of logic channels for the transporting the data coming from the different sources. In this session, we are discussing issues related to the physical layers and transmission medium that is controlled by the physical layer. We also discuss the structure and the physical layers of the telephone network and the cable network in the later part of this topic, physical layer. So our unit 2 is a physical layer, and we are going to start the discussion of the basic topic, basis for a data communication. Topic is data and signals. So one of the major functions of the physical layer is to move data in the form of electromagnetic signal across the transmission medium. The transmission medium in any form, wire, wireless or optical. Whether you are collecting the numerical statistics from the another computer, sending animated pictures from the design workstation, or causing a bell to ring in distant control center, you are working with a transmission of data across the network connection. Generally, the data usable to the person or the application are not in the form that can be transmitted over the network. For example, the photograph must first be changed to a form that transmission media can accept. The transmission media work by conducting energy along the physical path. So we can say that to be transmitted, data must be transformed to the electromagnetic signal. So what are the signals we are discussing? The first point is analog and digital. Both data and the signals that represent them can be either analog or digital. The data can be analog or digital. The term analog data refers to the information in the continuous, and the digital refers to the information that is a discrete state. The analog data take on the continuous values, whereas the digital data take on a discrete value. As you have already seen in our previous semesters, that the difference between analog and digital is a one simple waves. Just like for an analog signal, a sine wave is there. For the digital signal, a square wave is there. So some topics in this session we are going to see the analog and digital data, analog and digital signals, periodic and non-periodic signal. So analog and digital data. As we have discussed earlier that what is an analog and what is a digital, we can say that the digital clock can report the hours and the minutes which change suddenly from 8/05 to 8/06. So it cannot display the 8/0 5.5. Fine. So in analog data, such as sounds made by the human voice take on a continuous value. When someone speaks, an analog wave is created in the air. This can be captured by the microphone and converted to the analog signal, or the sample or converted to the digital signal. As you are listening my voice, it is an example of a analog signal which is converted by the microphone for the digital transmission. The digital data can take a discrete value. For example, the data are stored in the computer memory in the form of zeros and ones. They can be converted to the digital signal or the modulated into the analog signal for the transmission across the medium. So we can say that the data can be analog or digital. The analog data are continuous and take continuous waves, and the digital data have a discrete states and take a discrete value. Second, what is analog and digital signals? Like the data they represent, the signal can be either analog or digital. The analog signal has infinitely many levels of intensity over the period of time. As the wave moves from the value A to B, it passes through and includes the infinite number of values along its path. The digital signal, on the other hand, can have only limited numbers of defined value. Although each value can have any number, it is often as a simple of zeros and ones. The simplest way to show the signals by plotting them into the pair of perpendicular axes. The vertical axis represents the value or a strength of the signal, and the horizontal axis represents time. Figure shows an analog signal and a digital signal. It is our analog signal and it is our digital signal. So it is a comparison of analog and digital signals. The curve representing the analog signal passes through the infinite number of points. The vertical lines of the digital signal, however, demonstrate the sudden jump that can signal makes from one value to another value. So it is a vertical line, it is sudden jump from one level to the another level. Fine. So we can say that the signal can be analog or digital. Analog signals can have an infinite number of values in the range, and the digital signals can have only limited numbers of value, as we are seeing this. Periodic and non-periodic signal. Both analog and digital signals can take one of the two forms, periodic or non-periodic. Sometimes aperiodic because of the prefix A. The periodic signal completes a pattern within a measurable time frame called as a period, and repeats the pattern over the subsequent identical periods. The completion of the one full pattern is called as a cycle. The non-periodic signal changes without exhibiting the pattern or the cycle that appears over the time. Means in our periodic signal, we can say that it have one identical cycle which repeats itself after some time. In the non-periodic signal, there is no particular format for repeating a particular waveform in a given time. Both analog and the digital signals can be periodic or non-periodic. In the data communication, we commonly use the periodic signals because they need less bandwidth, and the non-periodic signals as the digital signals because they can represent variation in data. Fine. So we can say that in the data communication, we commonly use periodic signal, analog signal, and non-periodic digital signal. Second topic, periodic analog signals. The periodic analog signals can be classified as a simple or a composite. A simple periodic signal, analog signal, a sine wave, cannot be decomposed into the simpler signals. The composite periodic signal, analog signal, is composed of multiple sine waves. Over here, topics we have discussed, we are going to discuss the sine wave, wavelength, time and frequency domain, and composite signals. So first is sine wave. As you already know that it is a sine wave, particular cycle is there, it is a one cycle. After this same shape is repeating. The sine wave is the most fundamental form of periodic analog signal. When we visualize, it is a simple oscillating curve. It changes over the course of cycle in a smooth and consistent and continuous rolling flow. Our figure shows the sine wave. Each cycle consists of a signal R above the time axis followed by the single R below it. A sine wave can be represented by the three parameters: the peak amplitude, the frequency, and the phase. These three parameters fully describe the sine wave. So first of all, define the peak amplitude. What is the peak amplitude? The peak amplitude of the signal is the absolute value of its highest intensity proportion to the energy it carries. For electric signal, the peak amplitude is normally measured in a volts. Figure shows the two signals and their peak amplitudes. Over there, a yellow label shows the peak amplitude, means a maximum value of our wave is called as a peak amplitude. Let's have an example. The power in your house can be represented by the sine wave with the peak amplitude of 155 to 170 volt. However, it is common knowledge that the voltage power in our homes is nearly the given voltages. This dispensary, due to the fact that there is a root mean square values, the signal is squared and then the average amplitude is calculated. The peak value is equal to 2 raised to 1/2 into RMS value. Another example, the voltage of the battery is constant. This constant value can be considered as a sine wave. As we will see later, for example, the peak value of a AA battery is normally 1.5 volt. Period and frequency. The period refers to the amount of time in seconds a signal needs to complete a one cycle. Means over here, a time required to complete a one cycle is called as a period. So starting from the initial value, then it complete its cycle is called as a period. Frequency refers to the number of periods in 1 second. Means suppose we can take 1 second over here, it is a 1 second. So how many times the period takes to reach this 1 second is called as a frequency. Note that the period and frequency are just one characteristic defined in a two-way. Period is a inverse of frequency and the frequency is a inverse of period. As following, we can say that it is a equation: f is equal to 1 upon t and t is equal to 1 upon f. So frequency and time are inverse of each other. Figure shows the two signals and their frequencies. Two signals with the same amplitude and phase but different frequency. Over here the frequency is higher, over here frequency is lower. Means at some instant of time the cycle passed in this time is higher than this. Means suppose in the higher frequency it have 12 waves and over the lower frequency it have 6 waves. As the unit defined that it is a 12 Hertz, it is 6 Hertz. The period is formally expressed in seconds and the frequency is formally expressed in the hertz. As you already know, which is cycle per second. The units of the period and the frequency are shown in the table. Fine, it is very easy. Milli means 10 raised to minus 3, micro minus 6, nano 10 raised to minus 9, pico 10 raised to minus 12, kilo 3, hertz, mega 6, giga 9, tera 12. So, one example is that the power we use at the home can be frequency of 6 hertz. The period of this sine wave can be defined as t is equal to 1 upon f, 1 upon 60 is equal to 0.0166 second. So we can say that it is a 16.6 millisecond. This means that the period of our power for our lights at home is 16.6 millisecond. Our eyes are not sensitive enough to distinguish the rapid changes of amplitude. Another example. Express the period of 100 millisecond in a microsecond. From the table we have find that the value of 1 millisecond is 10 raised to minus 3 and 1 second is 1. It is a m is there. So 1s is equal to 10 raised to 6 microsecond. We make the following substitution. We are get this 10 raised to 5 microsecond. First, it is another example, just for understanding purpose. So, we already know that the frequency in the relationship of the signal to the time, that the frequency of the wave is a number of cycles it completes in a 1 second. But another way to look at the frequency is the measurement of the rate of the change. Electromagnetic signals are oscillating waveforms, that is, they fluctuate continuously and periodically above and below the mean energy level. The 40 Hz signal has an 1/2 of the frequency of the 18 Hz signal. It completes the 1 cycle in the twice time of the 18 Hz signal. So each cycle also takes twice as long as to change from its lowest to the highest voltage level. Frequency through describes in a cycle per seconds in general measurement of the rate of the change of the signal with respect to time. So we can conclude that the frequency is the rate of the change with respect to time. The change in short span of the time means higher frequency. Change over the long span of the time means low frequency. If the value of the signal changes over the very short time span, the frequency is high. If changes over long time, frequency is low. So there are two extremes. What if a signal does not change at all, or what if it maintains a constant voltage level over the entire time it is active? In such a case, it is a frequency is 0. Conceptually, the idea is the simple one, that if the signal does not change at all, it never completes a cycle, so its frequency is 0 Hz. But if the signal changes instantaneously, what if it jumps from one level to the another level in no time? Then its frequency is infinite. In the other words, when a signal changes instantaneously, its period is 0, since the frequency is inverse of period. In this case, the frequency is 1 upon 0, which is infinite, or we can say that unbounded. So if a signal does not change at all, its frequency is 0, and if the signal changes instantaneously, its frequency is infinite. Next is phase. What is phase? The term phase describes the position of the waveform relative to the time 0. If we think of the wave as something that can be shifted backward or forward along the time axis, the phase describes the amount of that shift. It indicates the status of the first cycle. So The phase describes the position of the waveform relative to the time 0. The phase measured in the degree or radians, 360 degree or 2 pi radian, 1 degree is equal to 2 pi by 360 radian, and the 1 radian is 360 by 2 pi. The phase shift of 360 degree corresponds to the shift to the complete period, and the phase shift of 180 degree corresponds to the shift of the 1/2 of the period, and the phase shift of the 90 degree corresponds to the shift of the 1/4 of the period, as you can see in this figure. So it is a 0 degree phase shift. The signal our signal starts over here. It is a 90 degree phase shift, or 1/4 of the t. It is a 180 degree, means 1/2 of the t. So these three sine waves of the same amplitude, but frequency is same, but the different phases. Fine. So you understand the phase concept with this figure, that each have a different degrees of a phase. Looking at the figure, we can say that the sine wave with a phase of the 0 start with the time 0 with a 0 amplitude, and the amplitude is increasing. Second, a sine wave with respect to the phase of 90 degree start with the time 0, which is peak amplitude value, and the amplitude is decreasing. The arrow shows the direction of the waveform. Third, a sine wave with the phase of 180 degree start with the time 0 with a 0 is 0 amplitude, and the amplitude is decreasing because our cycle completes on this direction. Another way we can look at the phase in the terms of the shift or offset. We can say that a sine wave with the phase of the 0 is not shifted. A sine wave with a 90 degree shifted by the 1/2 cycle. However, note that the signal does not really exist before the time 0. Fine. Third, a sine wave with a phase of 180 degree is shifted by the 1/2 cycle, and however, note that the signal does not really exist before the time 0. Fine. So let's have an example. A sine wave is offset have a 1/6 cycle with respect to time 0. So what is the phase in the degrees and radian? We know that one complete cycle is a 360 degree, and therefore 1/6 cycle is equal to 1/6 into 360. So we find that pi by 3 radian, and we can say that it is a 1.046. This equation is familiar to you. Wavelength. A wavelength is another characteristics of the signal traveling through the transmission medium. A wavelength binds the period of the frequency of a simple sine wave to the propagation speed of the medium, as you can see in this figure. Figure shows the direction of the propagation and the transmission medium at time t and t plus 1. While the frequency of the signal is independent of the medium, the wavelength depends on both the frequency and the medium. Wavelength is a property of any type of signal. In the data communication, we often use the wavelength to describe the transmission of the light in the optical fiber. The wavelength in the distance a simple signal can travel in a one period. A wavelength can be calculated in one of the given propagation speed, the speed of the light, and the period of the signal. However, since the period and the frequency are related to each other, and if we represent the wavelength by lambda, the propagation speed by c, speed of light, and the frequency by f, we can get wavelength is equal to propagation speed into period is equal to propagation speed upon frequency, because the period is inversely of frequency. So we can write that the lambda is equal to c by f, or c into period. So the propagation speed of the electromagnetic signal depends on the medium and on the frequency of the signal. For the example, in the vacuum, the light is propagated with the speed of 3 into 10 raised to 8 millisecond. That speed is lower in the air and even lower in cable. The wavelength is normally measured in the micrometers, microns instead of meters. For example, the wavelength of the red light frequency f is equal to 4 into 10 raised to 14 in the air is, so the lambda is equal to c by f. We get 0.75 micromillimeter. In the coaxial or the fiber optic cable, however, the wavelength is shorter, 0.5 micrometer, because the propagation speed in the cable is decreased. Fine. So up to now, wavelength and frequency is discussed. The time and frequency domain. A sine wave is comparatively defined by the amplitude, frequency and phase. We have been showing a sine wave by using what we call the time domain plot. And the time domain plot shows the changes of the signal amplitude with respect to time in the amplitude versus time plot. Phase is not exactly shown in this time domain plot. To show the relationship between the amplitude and the frequency, we can use that the called is frequency domain plot. The frequency domain plot is concerned with only the peak of the value and the frequency. Changes of the amplitude during the one period are not shown, as you can see in this figure. Figure shows the signal in the both time domain and frequency domain. It is our signal in the time domain. It is signal over our frequency domain signal. So only peak is shown there. It is obvious that the frequency domain is easy to plot and conveys the information that one can find the time domain plot. The advantage of the frequency domain is that we can immediately see the value of the frequency and the peak amplitude. The complete sine wave is represented by the one spike only. The position of the spike shows the frequency at its high, shows the peak amplitude. Fine. So we can conclude that the complete sine wave is in the time domain can be represented by the one single spike in the frequency domain, as we have seen in our figure. Let's have an example. The frequency domain is more compact and useful when we are dealing with more than one sine waves. For example, following figure shows the sine wave each with different amplitude and frequency. All can be represented by the 3 spikes in the frequency domain. Fine. So over here the constant value is there. So maximum signal value can be represented by this blue line. The waveform have a 15 value. Another pink graph shows the 10 amplitude value in this single spike, and the green line or green graph shows the value of 5 amplitude signal. Over here 0, 8 and 16 are shows the frequency. Composite signal. So what is a composite signal? So far we have focused on the one simple sine wave. A simple sine wave have many applications in the daily life. We can send a sine wave or single signal wave to carry the electrical signal from one porous to another. For example, the power company sends a signal sine wave with a frequency of 60 Hz to distribute the electric energy to the house and businesses. And another example, we can use a single sine wave is sent to alarm to security centers when a burglar opens the door of the window of the house. In the first case, the sine wave is carrying the energy. In the second case, sine wave is carrying a signal of danger. If we had only one signal sine wave to convey the conversation over the phone, it would make no sense and carry no information. We would just hear a buzz. As we will see in the further chapters, that we need to send a composite signal to communicate the data. A composite signal is made of many simple sine waves. So we can say that a single frequency sine wave is not useful in the data communication. We need to send a composite signal, a signal made of many simple sine waves. A composite signal can be periodic or non-periodic. A periodic composite signal can be decomposed into the series of simple sine waves with a discrete frequencies that have integer values of 1, 2, 3 and so on. Fine. A non-periodic signal can be decomposed into the combination of infinite number of simple sine waves with a continuous frequencies that have a real value. So we can say that if the composite signal is a periodic, the decomposition gives the series of the signal with the discrete frequencies. If the composite signal is a non-periodic, then the decomposition gives the combination of the sine wave with the continuous frequencies. Let's have an example. A particular figure shows the periodic composite signal with a frequency f. This type of signal is a not a typical to those found in the data communication. We can consider it to the 3 alarm system, each with have a different frequency. The analysis of the signal can give us the good understanding to how to decompose the signal. It is very difficult to manually decompose the signal into the series of the simple sine waves. However, there are tools, both hardware and software, that can help us to do the job. We cannot concentrate about how it is done. We are only interested in the result. Our figure shows the result of the decomposing the above sine signal in the both time and frequency domain. So this signal is decomposed with time domain and frequency domain. Right? 1 frequency, 2 frequency, 3 frequency. 1, 2 and 3. It is a third. Right? The amplitude of the sine wave with the frequency f is almost the same to the peak amplitude of the composite signal. The amplitude of the sine wave with the frequency of 3f is a 1/3 of the first, and the amplitude of the sine wave with the frequency of 9f is a 1/9 of the first. Fine? The frequency of the sine wave with the frequency f, which is the same frequency of the composite signal, called as a fundamental frequency or the first harmonic, a pink value. The sine wave with the frequency 3f has a frequency of 3 times of the fundamental frequency, and it is called the third harmonic. And the third wave with the frequency of 9f is a frequency of the 9 times fundamental frequency. It is called the ninth harmonic. Note that the frequency decomposition of the signal is a discrete in the frequency domain, f, 3f and 9f. Because of its integer number 3f, 9f and also integer numbers, there are no frequencies such as 1.2f, 2.6f, etc., etc. The frequency domain of the periodic composite signal is always made of the discrete spike as shown in this figure. Let's have an example. A figure shows the non-periodic composite signal. It can be the signal created by the microphone or the telephone set at when the word or the two is pronounced. In this case, the composite signal cannot be periodic, because that implies that we are repeating the same word or words with exactly the same time. In the time domain, the frequency representation or the time domain representation of this composite signal, there are an infinite number of simple sine waves or sine frequencies. Although the number of frequencies in the human voice is infinite, the range is limited. The normal human being can create a continuous wave of frequency between 0 to 4 kilohertz. Note that the frequency decomposition of the signal yields a continuous curve. There are infinite number of frequencies between 0.0 to 4000. To find the amplitude related to the frequency f, we draw the vertical line f to increase the envelope curve, and the height of the vertical line is the amplitude of the corresponding frequency. Right? The dot is shown over here. Bandwidth. The range of the frequency contained in the composite signal is called as a bandwidth. The bandwidth is a normally difference between the two numbers. For example, the composite signal contains a frequency between 1000 to 5000. The bandwidth is 5000 minus 1000 is equal to 4000. Fine? The bandwidth of the composite signal is the difference between the highest and the lowest frequency contained in that signal. A figure shows the concept of the bandwidth. The figure the two composite signals, one periodic signal and another non-periodic signal. The bandwidth of the periodic signal contains all integer values between 1000 to the 5000. The bandwidth of the non-periodic signal has the same range but frequency are continuous. Let's have an example. If the periodic signal is decomposed into the 5 sine waves of the frequency 100, 300, 500, 700, 900, then what is the bandwidth? Draw the spectrum and assuming all the components have the maximum amplitude of 10 volt. So here fH can be highest frequency and FL is the lowest frequency. B is the bandwidth. So the equation B is equal to fH minus FL, 900 minus 100 is equal to 800. The spectrum have only 5 spike, 100, 300, 500, 700 shown in figure. Fine. And bandwidth shown here is 800. Another example. A periodic signal has a bandwidth of 20 Hz. The highest frequency of the is 60 Hz. What is the lowest frequency? Draw the spectrum of the signal contains all the frequency of the same amplitude. We can solve this by fH is equal to highest frequency, FL is equal to lowest frequency, and the B is equal to this fH minus OFL. You can get this answer. The spectrum contains all integer frequencies is over here, and we can say that it is our spectrum. Another example shows the non-periodic composite signal had a bandwidth of 200 kilohertz with a middle frequency of 140 kilohertz and the peak amplitude of 20 watts. The two extreme frequencies have an amplitude of 0. They draw the frequency domain of the signal. So the lowest frequency must be 40 kilohertz and the highest frequency must be 240 kilohertz, and the figure shows the frequency domain and the bandwidth. Fine. So there are various examples of this bandwidth. So one last example is there. An example of non-periodic composite signal is the signal propagated by the AM radio station. In the United States, the AM radio station is assigned 10 kilohertz bandwidth, and the total bandwidth dedicated to AM radio ranges from 530 to 170 kilohertz, and it will show the rationale behind the 10 kilohertz bandwidth in the letter. So read these two examples. So we conclude our session with this question and answer, and we also summarize our session. What we have seen, which is shown over here, that we have seen analog and digital data, analog and digital signal, periodic and non-periodic signals, sine wave, wavelength, time and frequency domain, composite signals, and lastly a bandwidth. Write down the following question in your notebook and send back it to me as per the given direction. Thank you, student. See you in the next session.